To help understand this formula, we're going to go through using this formula to define the determinant for 2x2 matrices. And on your homework, there's a question where you can define the determinant for 3x3 matrices using this definition. Now, this definition does not look like what we used in A22. And if you don't fully understand this definition, that's okay. You can keep using the definition we learned in A22. This is just another definition. Okay. Now, we've got a few other definitions here that also work. We've got the cofactor expansion along a row, we've got the cofactor expansion along a column, and we've got multilinear and alternating functions such that the determinant of I is 1 for the rows of a matrix, and we also got this for the columns of a matrix. Any of these expressions can be used to compute the determinant of a linear or of a matrix. What we're going to do is we're going to use the expression to compute the determinant of a 2x2 matrix. Okay. So here we've got A11, A12, A21, A22. We want to take the determinant of this matrix. Okay, well, this equals the sum of sigma in Sn sine of sigma times A1 sigma 1 A2 sigma 2. Well, this equals the sine of sigma 0 A1 sigma 0 1 plus A2 sigma 0 2. Well, this equals plus the sine of sigma 1, A1 sigma 1 of 1, A2 sigma of 2. This equals 1 times A1, and sigma 1 of 1, or sigma 0 of 1 is 1. A2, sigma 0 of 2 is 2. Plus, the sine of sigma 1 is minus 1. A1, sigma 1 of 1 is 0. A2, or sigma 1 of 1 is 2, and sigma 1 of 2 is 1. So it's A12, A21, which equals A11, A22 minus A12, A21, which is our definition for the determinant. So we're happy with this. Now that we have our definition of the determinant, we can compute the determinant of our rotation matrix. The determinant of A equals cos squared minus negative sine cos squared theta minus negative sine theta times sine theta, which equals cos squared theta plus sine squared theta, which equals 1. So the determinant for rotation matrix is 1. Now, turns out this determinant of the rotation matrix equal 1, we can define rotation matrices in general using this condition. An n by n matrix is a rotation matrix, or an n by n real matrix is a rotation matrix if the determinant of A equals 1 and A times A transpose equals I. You can also see these as our real unitary matrices. So it gives us another name for our real unitary matrices. As a suggested exercise, we can use our definition of the determinant to show that the area of the parallelogram defined by the columns is the determinant function. And as a suggested exercise, which is also your homework question, is to verify the determinant formula for 3x3 matrices using this permutation matrix. Now that we have defined the determinant, now someone might calculate it. I want to review a few basic properties that we'll be using. So the first property is that we are n linear. What this means is that the determinant of A1, A2, up to CAN plus A, or AJ plus AJ hat to AN equals C determinant of A1, A2 up to AJ up to AN plus the determinant of A1, A2 up to AJ hat to AN. We are multilinear in that term, or n-linear. Another property is that the determinant of A equals 0 when two rows are the same. This is alternating. Okay. If A hat is obtained from A by interchanging rows, then the determinant of A hat equals minus the determinant of A. Again, alternating. Turns out that these two definitions are equivalent definitions for an alternating function. Now, the next property is quite interesting. The determinant of A transpose equals the determinant of A. So adjoints have the same determinant. Okay. Now, if A inverse exists, then the determinant of A inverse equals 1 over the determinant of A. This follows from 6 that says the determinant of AB equals the determinant of A times the determinant of B. Okay. This statement we proved in our homework. Using this statement, I would expect that you'd be able to prove this statement. Using 6, I'd expect that you'd be able to prove 5. And the last one has to do with block matrices. A, B, 0, C. The determinant of the matrix A, B, 0, C is equal to the determinant of A times the determinant of C. And the assumption here is that A and C are both square matrices, because we only have a definition for the determinant right now for square matrices. Okay. Now, a corollary of 6 is our following statement, that similar matrices have the same determinant. So B equals P inverse AP, which implies that the determinant of B equals the determinant of P inverse times the determinant of A times the determinant of P, which equals the determinant of P inverse times the determinant of P times the determinant of A, which equals the determinant of P inverse P times the determinant of A, which equals the determinant of I times the determinant of A, which equals 1 times the determinant of A, which equals the determinant of A. So similar matrices have the same determinant. The last thing that we do is we define the adjugate matrix of A. The adjugate matrix of A is defined by the ijth entry of the adjugate matrix is computed by taking the determinant of the ijth minor, or the ijth minor. To compute the ijth minor, what we're going to do is if we take a matrix, we cancel out the ith row, and we cancel out the jth column. And we get rid of those entries. And we take the determinant of what's left. And this is done in our cofactor expansion. With the adjugate matrix, what we're doing is, instead of using that row and column to compute our determinant, we're actually going to take whatever that minor is, and that gives us the entry in our matrix. Okay. Now, this adjugate matrix is incredibly useful because of the following relationship, which we leave as a suggested exercise. A times the adjugate of A equals the determinant of A times I, which is equal to determinant of A, determinant of A, determinant of A, 0, 0. It gives us this matrix. That relationship will be useful down the road. Again, when we're looking at these Determinants, the big thing that I want you to have is I want you to have an understanding of how to compute the determinant. So that's going to be practice, which is going to be that mathematics course I'm putting together, as well as these core basic properties. Similar matrices have the same determinant. The determinant of the transpose matrix, so remember this is the transpose, not the inverse, is the determinant of the original matrix. And the determinant of the inverse equals 1 over the determinant of the original. Those are the properties that I want you to know. I want you to know how to compute a determinant.